Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to my YouTube channel. And this is the most long-awaited video, which is about QTAIM analysis, or in simple terms, you can also call it AIM analysis, that is based on Bader's theory of atoms and molecules. And before we start using multi-WFN directly for doing the QTAIM analysis, let's first understand what this method actually means in some simple terms. So I have made a very brief presentation. These are very simple slides, which will tell you about some basics, which you should know before performing an acute time analysis, and then you can be able to write for a paper or for an assignment or whatever you want about this analysis, and you will be a bit more confident. So this is a very basic introduction, which will just make you able to jump into this field. And then if you want to do more, you can, of course, read some literature and yeah, upgrade yourself to be more confident while writing for research papers. So what is QTAIM? It basically stands for Quantum Theory of Atoms and Molecules, which is a concept developed by Richard Bader. And the main idea is that we can understand chemical bonding and interactions directly from the electron density that surrounds the atoms in a molecule. So in QTAIM, a molecule is divided basically into two regions that belong to each atom. And then based on how the electron density changes in space, we look for different things in it. So this helps us describe the atoms and bonds without relying on classical ideas like you know about the shared electrons or Lewis structures. So this this QTAIM is basically completely depending on quantum mechanics. So the key concept is the bond critical points, which will also be called BCPs as a short form. And you can think of it as a special point between two atoms where the electron density reaches a kind of balance. So it's not too high, not too low. It's like the bridge where two atoms connect through their electron cloud. So imagine a bond, and then in the center of the bond, there is a point where the electron density is balanced between these two. So that is called the bond critical point. And by analyzing the properties of this electron density at these BCPs, for example, we have its BCP electron density rho value, its Laplacian or its energy density. We can tell what kind of bond or interaction it is, whether it's a covalent bond, an ionic bond, a hydrogen bond, or whatever. So this is very important that you understand the basics. For example, in a covalent bond, the electron density at BCP is high and concentrated between the atoms. While in a hydrogen bond or van der Waals interaction, the electron density is much lower and the Laplacian is also positive, which means it's a weaker and a non-covalent interaction. So QTAIM basically gives us a quantitative, visual, and universal way to understand bonding, no matter what kind of bond it is. So now we talk a little bit about CPs. What are these critical points? So you will encounter different types of CPs in QTAIM. So it looks at the electron density, which is rho r, in a 3D space and identifies the critical points where and places where is the gradient of electron density. That is called Laplacian after all. So that means electron density doesn't increase or decrease in all directions. It's locally flat. So that's the critical point. And each critical point describes a physically meaningful feature of the molecule, like a nucleus, a bond, or a ring. So you can have many different kind of CPs, and we label them as omega or sigma. Omega is the rank, which is number of non-zero curvature. So this is basically a bit of technical stuff, but you will have the CPs, which will be like 3 minus 3, 3 minus 1, 3 plus 1. So it is talking about that. So the first three is the rank, and the second number is a signature. So that can be plus or minus. So it's basically about the second derivatives of rho at that point. So we're not going to go into any mathematics or so complex terms. So I'm trying to give you a very simple, a generic idea of this QTAIM. And yeah, so you can think of these CPs as describing how the electron density curves like hills and valleys around that point. So you can imagine it like hills and valleys between them. And yeah, so now we will have four different kinds of critical points. Uh, and it's important to know their names at least. So you, when you look at them in multi-WFN, you know what's going on and what you really want. So there are three -3 type critical points, which is the nuclear critical point. So this is basically found at the nucleus. So it is where the electron density is maximum, usually that is at the nucleus. And you can imagine as it as a simple picture, like it's a 3D hilltop of a row. You're looking from the top on a hill, so it's look like that critical point. And then this is 3 and 3 minus 1, which is the most important and which we will be looking at the most. That is a bond critical point. And that is a saddle point of the electron density, which is maximum along the bond path, but minimum in the directions perpendicular to it. So imagine a bond is like this. So it between two atoms, this electron density is maximum, but on the other sides, on the sides, it's uh, it's minimum. So it's like a mountain pass between two peaks. So there are two mountains and you are in between them. It's like a passage between them, and you can look at both sides and you know like what kind of path it is. And then there are 3 plus 1, which is a ring critical point. So this will be basically found in the rings. And then 3 plus 3, which is a cage critical point. So it's like in cage-like structures, for example, fullerenes, adamantines, etc. So yeah, so these are all different kinds. We will be more interested in the bond critical point, and that's what we will extract from the files. So now we let's summarize it. So you have learned about these different kinds of critical points, and we will be looking at these ones in more details. And yeah, that's a kind of a pictorial representation, how you can understand it. So this 3 minus 1 is like going between two hills, and then you can look on either side. So this is basically a little bit of summary I prepared to interpret these chemical interactions, which we will need later on. So yeah, it tells like if this value is in this range, what kind of bond it is. So I'll just minimize it and let's jump into doing some QTAIM analysis. So I have prepared this molecule. This is an acetic acid dimer. It's an interesting example where you can find the hydrogen bonding as well as other covalent bonds. So we'll try to look at this example. So I'll just drag this file into Multiwfn and press enter. So you got the Multiwfn menu. We need to go to this topology analysis. So I'll press number 2 and you see here, and then I press enter. And the next step is we're going to search CPs from given starting points. So, sorry, we are going to search CPs from the nuclear positions. Number 2, enter. And then we will look for search CPs from midpoint of atomic pair. So we're looking in between the atomic pairs. So number 3, enter. And now we're going to generate the paths connecting the 3 minus 3 and 3 minus 1 CP. So you can find two at one time. Like there is no way you can find just 3 minus 3. So we're getting or 3 minus 1. So we're getting both of them, these ones or the ring and cage ones. So we're interested in number 8. And now what we will do is modify or print detail or export paths or plot property along a path. -5. And then now we want only to retain bond paths and corresponding CPs connecting to two specific molecular fragments and remove the other bond paths which are not of interest. So how it works, I'll just move this one a bit on the bottom. So in Gauss view, let's have a look at the labels. And now you know that these are two different fragments. So it's very interesting when you have two different fragments and you want to know the paths between them or the interactions between those fragments, the non-covalent interactions specifically. And uh, in in other case, if you don't want to, like if you don't want to press anything, you just uh, you can press enter or press 0 and press enter and don't do anything here. But I'll just give it the two fragments path. So 1, 2, 3, 4, 5. So I'll say atom number 1 to 5 is one fragment. Oh, why it didn't accept it? Just a second. Oh yeah, I didn't write number 8 first and just wrote the fragment directly. So I'll go again -5 and number 8. So now it asks me to input atom list for fragment 1, which is atom number 1 to 5. And atom 2 is 6, 7, 8, 9, 10. So 6 to 10. Enter. And 16 bond paths have been deleted. Also delete corresponding BCPs. Yes. And now we will just return by pressing 0 from this menu. And here, if you want to visualize, you can see that you can press 0, and you can see that it has printed various bond paths. So we'll come back to it in a bit. And yeah, so now we will go to again this number 8, and then we can print and visualize the generated CPs, which are already there now. So here, if you want to make it clear, just remove this axis, and we are only interested in these ones. And so, yeah, these ones are the nuclear points. Let me show you. So I showed the molecule. Here it is. And now you can see CP labels. It gives you the labels for all the critical points. And if you remove these ones, you only have these two because we gave it the fragments. So it gave us this critical points between fragments and removed these covalent bond, which you already know that there is a bond. So you don't really need those critical points. But if you are interested, when it asks you to delete those fragments, you can say no, and it will keep these ones as well. And now you can also say atom labels, and I'll just move the molecule a little bit to make it more bigger. And yeah, so these ones are 11 and 13, I believe. Let me just remove the molecule. No. How can I show it more clearly? Yeah, I don't think it's 11 and 13. You can have a look. Um, and size of the labels. Oh yeah, you can make it bold and then you can see 11 and 13. So now I want to save this picture as well. So I can just say save picture, and it has been saved to a file called dislin. So here it is. So I can rename it acetic acid dimer BCPs. All right, and I'll move it to the test folder. I will keep all the files at this test folder. And now we will just return from here, close it. And now we would just want to save all these CPs into a file. So that is, if I just press 7, enter. So it asks you for the index of CP you're interested in. I'll just say 0, which will save all the CPs to a cpprop.txt file. So yeah. So now you can see that it has saved this cpprop.txt file here. So here we are done with this window now. So I'll just minimize it. And now we open this cpprop.txt file and let's have a look at this file. So now we have the molecule on one side and we can keep this one here. And now you can see that it has given you all these the numbers. I'll just probably move this to the test folder and then open here. So now this is the picture we saved. I'll probably close this one and keep this one here, which is more convenient to discuss now. And then I'll keep this one here. So now you see that this is 11 and 13. So if we just see this is CP number 1, we move to CP number 11. Here you go. So it is a 3 minus 1. It's a bond critical point. It's between atom 2O and 10H. So atom O2 and 10H. So this CP is here, and you've got all its values in here. It's a bit tedious to extract values from here manually. So what I've done is I have created a script which is called extract aim data.py, and I have added it to the same repository where I have put the Multiwfn. You already have the link from the previous video. So if you go to this repository, you can see that it has this extract aim_data.py and this aim_data file.xls. This is the Excel file as well. This Excel file which we will use to copy the data. So I have given these two files to you, and I'll also put this acetic acid dimer fchk file just so you can practice and have the same numbers and everything. So what we will do is we will run this script which will extract the relevant data for us and give us a simple CSV file. So I can see Python 3 extract aim data and give it the name of the file, this file, the cpprop.txt. And I'll press enter. So it just extracted the data as a CSV file. Here you go. And if I just resize these columns, I can see that it has given me all this data. And now if I open this aim file, this file I prepared for you guys, so I'll just put it on the side. So I will just write here acetic acid dimer. And now we can see that where we were interested in only the 3 minus 1. So I'll just copy this data into here. So always keep these values only function, which keeps your formatting. And then this is also a 3 minus 1. Yeah. So here we go. Now we have this data here, and I'll just close this one. So now you have this file, and there is one more thing. Where is the acetic acid dimer? I'll just close this one. So if you look, you can also add the distance between atoms, which can be useful in some cases. So for example, this one was between 2O and 10H. So if we look at the labels, 2O and 10H, the distance is this one. I copy this and paste it here, and then 5H and 7O, this one. Yeah, so now we will just save this, and yeah, so now we've got all these values. The next step is to decode these values. What do they really mean? So I'll just arrange this. Very sorry about the long video, but it was really necessary to keep everything in one place. So yeah, so now we will look at different things. You can see the density of all electrons. So you can see that the density of all electrons is here, which if it is greater than or equal to zero point 0.2, it's a covalent bond, and if it's between 0.03 and 0.06, that's a partial covalent bond. Hydrogen bond is a bit stronger than the other non-covalent interactions, so yeah, that's not less than 0.03. It's between this range, so you can see that it's 0.05, it's not covalent in this region. And then for hydrogen bond, the Laplacian is positive. So you can see that its Laplacian values are positive for both of these ones. And then the value of GR is, for covalent, its contribution is less than 35%, or for non-covalent, its contribution is greater than 35%. So you can see that it's 0.039, so it's almost 39%, which means it's greater than 35%. It's a non-covalent bond. And then the potential energy density in covalent case, the GR is less than VR. But here you can see that GR is not less than VR, it's greater than, so it's also supporting that this is a non-covalent bond. And then you have this ratio. You can study more about it in this article I have mentioned here, which is a nice article which explains things better. And it's present in this, the link is also present, its reference and its screenshot is present in this Excel file. And then you can also have the distance, bond distance. So this is a nice table that you can present in your manuscript, and then you can write a beautiful discussion about it, about this QTAIM analysis, or what kind of bond you have got. So I hope you would have learned something new, and this would help you in understanding the QTAIM analysis and the theory behind these interactions, and then the interpretation as well. And you would be able to write really nice QTAIM analysis sections in your manuscripts after watching this video. Thank you very much for watching. If you liked the video, please try to subscribe the channel and like the video and post a comment. That just encourages me to find more time and try to make some more videos. And I'll try to make next video about the NCI analysis. And till that time, I say you goodbye. See you in the next video.